Hello and good morning. This is my second attempt at this lesson. I just finished recording the whole thing and the software crashed as I was literally on the last question, 30 minutes in. Grrr! That's okay. Round two. It's going to be even better this time. So I hope you're all doing well. Just to bring you up to speed. So I'm at home sick. Woke up Sunday with a stuffy nose, sore throat, which is what I still have. And because of that, with COVID restrictions, I'm not allowed to come to school until I've had a COVID test and the results are negative and I feel fine. So I had my COVID test early this morning, which is actually Tuesday. I'm recording this for you guys. So hopefully I get those results back quickly and they're negative and I'm feeling better and then I'll be back in school. So I have no idea when that's going to be. The sooner the better, because I hate not being in the classroom with you guys. This is far less than ideal. However, we'll make the best of the worst, and we can use technology to our advantage. So your lesson for today, we're starting enthalpy. So you guys have a brand new booklet for notes, and that's what we're going to be working out of today. You have an excited substitute teacher who's there to work with you and help you guys out if you have some questions. She'll be watching the video too, so she's pretty smart. She'll have it all figured out after working through this with you guys. So I have some enthalpy memes on the front that may or may not make sense to you. Once you know this unit, they might make a little more sense. Okay, let's rock and roll. So in your notes booklet, we're going to go through this first section, and I'm going to break my video into two pieces today so that if it does crash, I don't lose such a big chunk of work, only half as much. Okay, so in your notes, first thing we're going to look at is major uses of energy derived from fossil fuels. So heating, electricity, and transportation are the three main uses that you can fill into your notes. So we burn hydrocarbons for all three of those. So we're burning methane in your homes to heat. So methane gas is being burned. To generate electricity in Alberta, we burn coal and oil and gas, natural gas to generate electricity. And about 90% of our electricity in Alberta is produced by burning coal, oil, and natural gas. And then transportation in our vehicles, we're burning octane and diesel C12, H26 in our cars for transportation. So those are our three main uses. Why are we concerned? Well, all three of those produce CO2 and H2O, greenhouse gases, global warming, and acid rain as a byproduct of the combustion. If there's any sulfur in there, we get acid rain, and nitrogen through the burning process. Nitrogen in the air makes nitrous oxides, acid rain as well. So we're looking for alternative energy sources. How can we use less hydrocarbons, decrease the hydrocarbons, and increase the alternative sources that are also potentially renewable? Because again, one of the issues with hydrocarbons is they're non-renewable. We're going to run out of them. So we got to come up with some alternatives. So alternative energy sources for heating, probably the best two are solar heating and in central Alberta, geothermal, where we drill down into the Earth's crust and tap the heat that's stored in there and bring it up to the surface to heat buildings. Okay, what else? Two energy alternatives for transportation. So alcohol or gasohol, and that's coming from fermentation of plants. So that's like a biofuel. Is that in here? No. So that's the term they'll sometimes use is biofuels. Let's see if I can enlarge this a bit. Biofuels and hydrogen fuels as well. And hydrogen, we get our hydrogen from splitting water with electricity into hydrogen and oxygen gas. So those are probably our best two alternatives for transportation. And, well, there's similar ones repeated: solar, nuclear, hydroelectric. These guys are more BC for hydro and Ontario, Quebec for hydro, and then nuclear is Ontario And just the other day in the news, they announced trying to come up with some small nuclear power plants that they can use in northern Alberta in the oil sands area. But that's 10 or more years away. Okay, let's motor on. All right, so some things to think about as we move through the unit. How does our society use the energy of chemical changes? And how do chemists determine how much energy will be produced or absorbed for any given reaction? That's really what this unit is all about. So we're going to look at some reactions you already know. Photosynthesis is the major natural contributor to stored energy on Earth. Okay, the sun's been shining for billions of years. Plants have been taking the sun's energy and combining inorganic carbon dioxide with water. And if you remember the balanced equation for photosynthesis, it's 6 of each, producing a glucose molecule. I'll put it as a solid, and 6 oxygen gas. So there's our photosynthesis. This has been happening for billions of years. We have a lot of stored energy on Earth in the form of glucose, which is then stored as polymers, as starch in plants. Long term, it's stored in fossil fuels because plants and the animals that ate the plants can be turned into fossil fuels over long term. Okay, is the energy absorbed or released in photosynthesis? So absorbed, is it coming in as a reactant, or released, is it a product? Hopefully you remember that it is absorbed as a reactant. So I'm going to put energy just like it was a reactant. Energy plus CO2 and H2O makes that. So it is absorbed. Okay, the opposite of this would be the chemical energy stored by plants is converted to usable energy by elves. Yes, by elves. By animals using cellular respiration. So what does cell resp look like? It's the exact opposite. Whoops. C6, H12, O6, or glucose is burned in our cells with 6 oxygen O2 gas. What a mess. 6 O2 gas molecules to make 6 CO2 and 6 H2O. I'm just going to speed along here, and these would be considered waste products. So what do we really get out of cell respiration? We get a bunch of energy produced. Energy. So we get energy as a product being released. So these are opposites. Absorbed for photosynthesis, released for cell resp. What are the products here? Are the reactants here. Okay, complete thing in reverse. Today's fossil fuels have their origin in the decaying plant. Plants become coal and natural gas, and animals become oil. So today's fossil fuels came from the stored energy in plants and animals from millions of years ago. So where did all of this energy originate from? It all comes back to sunlight. So sunlight here is the start of the formation of glucose, which is then stored in plants and used by animals and long-term decayed into fossil fuels. Holy smokes. So you got to remember that. Okay, motoring on. We're skipping that order. Fossil fuels, exploitation, and going straight to looking at photosynthesis and cell resp in detail. So now we're going to look at the energy of these reactions. Whoa. Photosynthesis. Okay, that one is, oh yeah, that's right. I don't know why I have energy over there. That's a mistake. Energy is on this side. Never noticed that when I did my first take of this lesson. Good thing we're getting version 2. Okay, so the question for you is this reaction endothermic or exo? Endo, entering, exo, leaving. Thermic means energy. Is the energy entering or leaving? Thanks, Bryn, you're right. It's entering, endothermic. Good. How can you tell? Well, it's entering on the energy side. Okay. You have to be able to look at an endothermic reaction using a potential energy diagram. Potential energy diagram for photosynthesis. How does this work? Well, it starts at low energy for an endothermic. And if we read across, this would be high. And this is potential energy in kilojoules, so our energy change. So what this is telling us is we're starting with low energy reactants and finishing with high energy products. So who has more energy stored in their chemical bonds or chemical potential energy? CO2 and H2O, the reactants, or glucose and oxygen, the products? Correct answer? You bet. That is correct, Julie, the products. Glucose and oxygen, and you can see it here. This increased delta H means energy or change in energy is stored in the products. So we know that glucose and oxygen are pretty high energy, and that's the energy gained from photosynthesis. Okay, I got to talk about this first. Key little concept, and this is in your notes, I believe. Yes. Potential energy is stored energy. So when we say chemical potential energy, that's stored chemical energy, and it's stored within the covalent bonds of the molecule. Or if it's ionic, it's stored in the ionic bonds. And it's also between molecules with intermolecular forces. So London forces, dipole-dipole, hydrogen bonding, all of that contains energy as well. But this is the one that we're going to be most interested in, is the covalent bonds of hydrocarbons, because we know that those are all covalent bonds, right? And there's a lot of stored energy in those carbon to hydrogen bonds, and that's what we're after when we combust it to get at that energy. So here's an example. This is cell respiration. You could think of this as a slow burn or a combustion of glucose, and there's a lot of stored energy in those bonds of a glucose molecule. When we burn it, the energy is released as a product. So, Cooper, is this endothermic or exothermic? You're thinking, what an easy question, Mr. Johnson. The answer is right there. Yes, it is exothermic. So, Cooper, is there more energy stored in the reactants or stored in the products of an exothermic reaction? Correct again, in the reactants. So we can see the reactants have high energy and the products have low energy. Where did the energy go? Well, it was released. Usually it's released to the surroundings. Where is most of the stored energy in cell resp? Reactants or products? In the reactants. Okay, and it's released as a product to the surroundings. So we would say the surroundings gain the released energy. And this is a key idea of enthalpy. It's keeping track of the energy in chemical reactions. Is it endothermic or exothermic? Is it gaining or losing? Who's gaining or losing? How much is being gained or lost? By the way, some of our AP Bio people, how much energy is given off by cell respiration for one molecule of glucose? One molecule, I think, what did we decide? Was it 36 ATP per molecule? And ATP is not an energy that we use in chemistry. That's biology. So in chemistry, we're interested in moles. 1 mole of glucose gives off 2,802.5 kilojoules of energy. Okay, that's quite a bit of energy. Glucose is a high energy compound. So if we were measuring this change in energy, the delta H would be 2,802.5 kilojoules. I think that's the right number. I'm going from memory. And we're losing it, so I'm going to throw a negative sign in front. That's a loss of energy to whatever it's going to. In a living cell, it's going to ATP. All right. How are we doing? Rolling along. We're almost at the halfway point here. Some definitions for you guys. So I'll blow these up a little bit, put in your notes. Thermochemistry is the study of energy changes. So we're on to the next page. Study of energy changes, and that can be produced or absorbed. Another way to look at it is loss or gain during a chemical reaction. Study of energy changes during a chemical reaction. When we look at these energy changes, we're looking at them in isolated systems. And an isolated system is one where matter and energy cannot enter or leave it. Okay? It is closed to both the transfer of matter and energy. So you could think of an isolated system as a really good thermos. A thermos where you put in, let's say, half a liter of hot chocolate at 80 degrees Celsius, and one day later, you open it up and you still have half a liter and it's still at 80 degrees Celsius. That would be a true isolated system. So thermoses are good, but they're not a perfect isolated system. Okay, calorimetry. So in this unit, we are going to be studying energy changes and transfers in isolated systems. So we'll be doing calorimetry, and we'll be using a calorimeter to do that. So this is the device that isolates a system. It's kind of like a thermos, and it allows us to measure heat flow. So here is a very simple calorimeter, which I'll scroll down to once you have those definitions. And it's just styrofoam cups or polystyrene. Polystyrene is a really good insulator. So we're going to use them to build our isolated system. It's 3 cups, 2 on the bottom, 1 on the top, a thermometer, and that will allow us to measure energy change by temperature. And they usually have water, and the water is what gains or loses the energy. So we can measure the temperature of the water. So energy change of water, and the water gains or loses energy. So usually the chemical reactions are happening in the water. And then here's our isolated system, polystyrene. In this case, it's 2 polystyrene cups on the bottom, 1, 2, and a single one as a lid to keep it closed. The beaker is optional to hold the cups in place. So this is the styrofoam calorimeters that we use in Chem 30 labs. As a side note, the unit that we use is joules, or, so it's capital J, or kilojoules. That's the unit of energy, SI, so metric or System International unit of energy, joules or kilojoules. You guys will be more familiar with calories, which is the old imperial system. So a calorie can convert to 4.18 kilojoules. So they say that the average adult needs about 1,500 calories a day, which converts to about 6,000 kilojoules a day in your diet. So when you're eating food and you're going, oh, this cookie is 100 calories, what does that really mean? Well, that means that that is 418 kilojoules of energy in that cookie. So it's kind of interesting. People are always talking about calories in food, but they're really talking about the stored energy in the chemical bonds of the food. And the more sugar, the more stored energy, because we know glucose is high energy compound. Okay, I just want to check. Okay, here we go. So last slide, then we're going to take a break for a little demonstration. Calculating the quantity of energy, or Q. So in thermal chemistry, we were interested in calorimetry and tracking the gain or loss of energy. So what do we have here? Heat, or thermal energy that is transferred within an isolated system. So we're going to focus on the heat transferred between water and a chemical reaction. So most of the reactions that we do happen in water, and we'll stick a thermometer in here to measure the temperature change of the water, because the water is going to gain or lose the energy that's happening from the chemical system. You can see Q gained or Q lost. So it can be a gain or a loss, depends if it's endo or exothermic. So we're interested in Q. Now, I'm going to tell you right now, I'm not a big fan of formulas for Chem 30. This is our formula for the quantity of energy being transferred. I don't use it, but the textbook does, and you'll see it. So I will go through the variables, because we do use the 3 variables, and you need to know the units. So Q is quantity of energy, and unit is kilojoules or joules. M in the formula represents mass of the material that's being heated. And yeah, you're writing these down. And it can be grams or kilograms, just like this can be joules or kilojoules. C will be a new unit for you guys, and this one is the specific heat capacity of the material. And it's an unusual one, so it is joules per gram degree Celsius. It doesn't look great here, but I write it like this: joules over gram degree Celsius, or kilojoules over kilogram degree Celsius. These are the same unit. I've just put the kilo in front. And I use this one when I'm given kilograms, and I use this one when I'm given grams. So the mass kind of determines which unit to use. What is specific heat capacity? So as it says here, the quantity of heat, or the joules, needed to raise or lower the temperature of a material 1 gram, 1 degree Celsius. So let's look at a couple numbers in this chart. Make sense of this unit. So here is ice, and here is its C, or specific heat capacity. This tells us that it takes 2.00 joules to raise 1 gram, 1 degree Celsius. If I wanted to heat up 2 grams, 1 degree Celsius, then I would times it by 2, because that would be times 2 grams, so that would be 4 joules to heat up 2 grams, 1 degree Celsius. Water is quite high at 4.19 joules to heat 1 gram, 1 degree Celsius. The lowest one on this chart, the lowest two, are metals. Metals don't take a lot of energy to heat them up, which is why they're good for cooking. Iron is 0.449. So that means 0.449 joules to raise 1 gram, 1 degree Celsius. So if you had a pot full of water on the stove, which would take more energy to heat up, the iron pot or the water sitting in the pot? And the answer would be the water. It takes far more, almost 10 times more energy to heat up water than to heat up iron. And copper is similar to iron. Most pots have copper bottoms. Some pots are made of aluminum. It's not as good, though. It takes twice as much energy to heat up as iron. The only problem is iron rusts, so that's why they go with copper. So metals have a low specific heat capacity, very little energy needed to raise 1 gram, 1 degree Celsius. Water's high. When you're given water in a question, you're often given it as a volume, and you need to convert it to a mass. So 1 milliliter converts to 1 gram, and 1 liter converts to 1 kilogram. So if you had 3.5 liters of water, you would say that's the same as 3.5 kilograms. And if you had 5.3 milliliters, that's 5.3 grams. Okay? Lots of theory, lots of sit and listen and do a little bit of thinking. Okay, delta T, change in temp. You've seen that one before. Which substance in the chart above requires more energy to heat up? Ice, water, aluminum, or iron? And the correct answer would be, the most energy to heat up would be water. It takes 4.19 kilojoules to heat 1 kilogram, 1 degree Celsius. And iron is the lowest. It only takes 0.449 kilojoules to heat 1 kilogram, 1 degree Celsius. If the same amount of heat is provided, which substance will have the largest change in temperature? So if we added 1 kilojoule of energy to all of these substances, which one would have the largest change in temperature? Iron, lowest specific heat capacity. Okay, and that brings us to our break. We're probably 2/3 of the way through the lesson. The incredible balloon demo. So your teacher is going to demonstrate this for you to illustrate the concepts of specific heat capacity. And I'm going to I'm going to finish my video here and then start my next one on a new one so that I don't lose all this work in case of a crash. So after the demonstration, I'll be back to give you the math behind this. So you guys are going to need your calculators for the second half of the lesson.